Hello and welcome to Algebra 2 with Mr. Clausen. Today we're going to get started on inverse variations and start this new unit on rational expressions. So to get started here, we'll talk a little bit about how to identify direct and inverse variations. We'll briefly talk about how to model them, how to apply that terminology when it's used to describe relationships between between variables, and then finish with a real-world modeling question. So without further ado, I want to get started here with talking about some of these basic examples. So how you identify a direct variation from a inverse variation is relatively simple, and direct variations, for example, look like y equals k times x. Well, y is a specific dependent variable, and x is the independent variable, and k is the constant of variation. Now, this constant of variation, since it relates to a direct function, would be the constant of direct variation, and then the inverse variation looks like y equals k over x, where again k is the constant of variation, but in this case would be the constant of inverse variation, but we can refer to k as the constant of variation in both of these given circumstances. So the main idea here is that we can look at a set of values like the three that I have here and then start to identify whether the relationship between x and y, the independent and dependent variable, is direct, inverse, or neither. All right, and all three are possibilities. So how do you do this? Well, typically what you do is, like, if you're wanting to check if something's a direct variation, you go y equals kx, and I'm actually going to set this equal to k because that's really the secret to looking at this variation. So we can say k is equal to y over x. This is how you find the constant of variation, and I just start looking at it and seeing what those values are. So if I go 14 over 3, and then I go 8.4 over 5, all right, and this is all the further I need to go because I'm just looking at these two values and I'm going, these are not equal to each other. And in order for this to be a direct variation, all these values have to be equal to each other. So this is how we would check for a direct function, and these don't equal each other. So we're just kind of put the kibosh on that, and now let's check the inverse variation. And what I will say is that as you get better at looking at these patterns, you'll know whether you just need to check whether it's direct and whether it's inverse to just make sure it's one or the other. And if it's not, then you just know it's neither. But in this given situation, if you want to check for the inverse variation, we just go y is equal to k all over x. And what I'm going to do in this case is multiply both sides by x. Those will cancel. And k is going to equal x times y. This will be the constant of inverse variation in this case. And so what I'm going to do here, again, looking at these numbers, is I'll go 3 times 4, or 14, sorry, and 5 times 8.4. Ooh, this is looking promising. 6 times 7, and 4 times 10.5. And what I will find is that if I multiply all these combinations, I will find that they all are equal. And what that tells me is that this is a inverse variation. Put a big check mark, whatever. And so we can look at this set of data, and it makes sense, right? As x increases, y decreases. That's the type of pattern, if you're looking at an inverse variation, that you would expect, because k is the fixed number, and as your denominator gets bigger on a fixed number, you expect the output to be smaller. Very typical of an inverse variation. Now let's look at this next function here, and go and say, let's check the direct variation again, and say k is equal to y over x. Look at that combination and just start plotting oh, sorry, I wrote that upside down there. Let's go 2 over 10. And just start penciling in some of these combinations. And, you know, I start looking at all these, and man, these look really similar. And I tell you what, if you start punching all these in with your calculator, which you should check, but what I will say is I did the math, and these are all 1/5. And so I can tell you right now that this is a direct variation. And just kind of go and check those out. So just looking at those, and I think it makes sense, right? As x is increasing, y is increasing, so you should expect that if it does have a constant of variation, it is a direct variation. Now, this isn't to say that every function that you will look at will consist of a direct or an inverse variation. There could be some specific geometric patterning that you could be dealing with other types of functions that are not necessarily going to be fitting into this. So, for example, you know, I have this set of data here, and so if we say y over x to check for the direct variation, and we start looking at some of these, I mean, you'd have 1 over 1, and 6 over 2, and 3 over 3, and 12 over 4. And we see that it's like every other, it's working out, but it's not for the whole thing. So this is some type of weird system that's not going to work in this type of situation. So we can't say it's a direct variation. Just not going to work. I'm not sure what's going on. I mean, the output is kind of, it might still be some type of function because each input has a unique output, at least based on the data that we have. But we don't know that for sure based on the data value that we have. And I'm also just going to look at the XY comparison as well. You know, 1 times 1, well, that's 1. 2 times 6, I already have a conflict of interest. 3 times 3, I already have a conflict of interest. 4 times 12. And none of these equal each other. And in terms of going from one term to the next, they're not equal to each other. So this is neither a direct variation or an inverse variation in terms of looking at these examples. So, but that's the trick, is you just got to understand the basics of what a direct variation is and an inverse variation and figure out, you know, does the set of data fit one of these patterns? All right, so now that we've talked about the basics of direct and inverse variations, I want to look at these two functions. Again, these are the same ones that we were looking at the previous slide, and we identified that this was a inverse variation and this was a direct variation. So we'll look at an example of how to create a model for both of these. So remember, for inverse variations, y is equal to k all over x. So if we want to find the constant of inverse variation, just multiply both sides by x and get it, k is equal to xy. And to find this, we'll just go 3 times 14. Now, I would check all of these when it's such a small data set like this, you know, to determine whether it's true or not, or at least write them out like I did in the previous slide, you know, and make sure, like, oh, okay, yeah, those are all lining up. I can tell this is an inverse variation. You know, we can go and assume that this is 42 as far as the constant of inverse variation and move on from there. Obviously, you know, you'll have circumstances where everything doesn't fit perfectly, especially when you start dealing with real world stuff, and we'll talk about that in a little bit here. But if you know the constant of variation is 42, you just plug that in for k, and your inverse variation is just y is equal to 42 all over x. This is the equation that models whatever this data represents. And it's that simple as far as creating a model at looking at that specific situation. Direct variations are the same thing, but remember that if you're told something is direct, this is going to be y is equal to kx. So the constant of direct variation in this case is going to be k is equal to y all over x. So in this case, you'll have 2 all over 10, and so on and so forth. And again, you should check it, but this will give us 1/5 as far as the constant of direct variation. And so you just go y is equal to 1/5 times x. And this is your equation that models this direct variation. And so hopefully that's a relatively straightforward concept in terms of these models and how we look at this given circumstance. Now, I want to look at a little bit about how to apply this terminology, and I'm actually going to apply this to the ideal gas law. So pull on a little bit on your chemistry knowledge here, probably from a year or two ago, but the ideal gas law was actually derived by combining multiple gas law relationships. And what people like Charles and Boyles and Avogadro found is not necessarily anything. I mean, they were profound in themselves. Don't get me wrong there. But they went and only found like one relationship at a time. So what, Boyle found, for example, is that volume was inversely proportional to pressure. This is what he found, and if you are trying to figure out what this alpha fish thing is, this is what we use for proportional. All right, so it's sort of like an equal sign, but it's implied that there's a hidden constant here. And so inversely proportional just means, hey, it's, as P goes up, V gets smaller. And that kind of makes sense, right? If you put a lot of pressure on a pop can, it just squashes. And, if we look at Charles' law, this explained that volume is directly proportional to temperature. So they said V is proportional to T. And then Avogadro's law, I'm just going to go Avo, he found that volume is directly proportional to the number of moles. And typically we use N for that. And so what we can do is, and what many of these scientists did, is someone went and took all three of these proportions and meshed them together into what's referred to originally as the combined gas law, but eventually evolved into the ideal gas law. And so what we're able to do is say, hey, V is equal to pressure on the bottom, inversely proportional, right? If it's inversely proportional, the value on the other side will be in the denominator, and if it's directly proportional, those values will be in the numerator. So we can go N, and we can go T, and so directly relational, inversely relational, and then because we're actually trying to derive an equation here, there will be a constant of variation, which we're going to input as K. So we're going to derive this equation that shows the volume of the ideal gas, and we're also going to identify the constant of variation based on the table of data that's provided here. Now, the reason I refer to K as the constant of variation, there might be a little bit of different opinion on this, but I just refer to this as the constant of variation because it can be present in equations that have both direct variations and inverse variations all combined. So that's why I like just to refer to it in that way. But if we now want to solve for this constant, well, we should rearrange the equation a little bit so that it equals K. So, what I'm going to do here is multiply both sides by P over NT. This, I know, is probably a fairly simple chapter 1 type skill, but you should still be able to do it. And we'll go PV all over NT. And now what we're going to do is we're going to plug this data that they have here. And so we're going to say 1.00 atmospheres with a volume of 22.4 liters. And I'm keeping track of the units because it does ask for the answer in units. And now we're going to go and say 1.00 moles times 273 Kelvin. And what you will find is that when you do the math here and you take 22.4 and divide it by 273, because the ones are just ones, you'll find that the constant of variation is equal to 0.08205 liters atmospheres per mole Kelvin. Pretty slick, huh? And this is how we found what eventually got referred to as gas constant R. So if you learn that in chemistry, or you take a high school chemistry course. You'll learn about this a little bit. And so what we get in the end is V is equal to nRT all over P is the relationship as we know it today, or you could say NKT all over P because K is still a constant, right? All these relationships can be combined together to go and find these relationships. And this is where the rubber meets the road. I mean, this is some really applicable stuff because if you can go and create linear models to explain things as fundamental as pressure, that is a significant relationship that can be used in the real world. So let's talk about one other real world modeling question. So here I have a table. In this table, don't take this as a promotion of the BMI values. I feel like this table is a little bit bogus, but everybody to his own opinion. So, but this is based on a set of different direct and inverse relationships in terms of the BMI. So it says the BMI is a relationship that directly varies with weight. So let's go weight in pounds, and is inversely relational based on the square of height. So it's height squared, and it doesn't say, but this should be inches. And you have some constant of variation, K. And what the table is going to ask you here is to use this portion of the BMI chart to determine the BMI formula. Okay, and so we have BMI, we could just treat this as Y, so to speak, just so we don't have this 3-letter acronym thing that we're trying to figure out, where height is H and pounds and weight is W. All right, that's how I have it labeled over here. And so, just like we did previously, to find this constant of variation, we just need to pick some values and to go for it. So I will say that 5'6", this is 60, so this is 66 inches, and then this is 67 inches, 68 inches, and you're just trying to do something that's relatively linear here. I would really avoid going 5.5 and, oh man, like thinking about 12ths in decimal form, just, let's keep the number really nice to work with here. So that's why I'm suggesting the inches. And then as far as the BMIs go, all we should really need to do here is, 19, I'm assuming, is corresponding with this, and 24 is corresponding to that weight. So we have some Y and X, well, I guess it's W and H values at our disposal here, so we can start calculating some of this out. So what I'm going to do is I'm going to rearrange this equation so that it equals K. So that means multiplying both sides by H squared and dividing both sides by W. So let's just leave Y as Y and multiply both sides by H squared, divide both sides by W, and this will equal the constant K. This is our constant of variation that we need to find in order to create the formula. So now I'm just going to pick some values and I'm going to see what happens here. So let's use 5'6" with a BMI of 19 and 118 pounds. All right, because the 19, my assumption, is going to correspond to that. So let's go. And I'm going to test a few values here and see about where that constant of variation is. So, if I go 19, that's going to represent the Y here. And I'm going to times it by 66 twice, times 66. And then I'm going to divide it by the pounds that the individual is. All right. And I'm going to get a K value equal to 701. I'm just going to round to the 10th place, 0.4. Now, if I look at someone closer to, my height and mass, I guess they don't even have my height on here. I'll go 6 foot. I I'm not 221. 293 is high, but we'll just go with that. So that would be a BMI of 39.9. It's still a big number. I mean, this is technically a pretty heavy category. And so now if we're looking at this and we try to find that, you know, the K in this case would just be the, you know, the BMI value, which we're going to go 39.9, and we'll multiply that by the height squared, all right, which, again, I'm taller than 72 inches, but we're just going to use that because that's what the table has there. And then we're going to divide it by 293. All right, so this is going to be 705.9. And let's do one more. So let's do 5'10" with a let's just go with 19. Actually, we'll go with 24.5. So that would be 173 pounds. And hopefully you're kind of seeing how I can use this table. That's probably half the trick with this particular problem. This is definitely a lot of data to look at, but part of the emphasis of this video is just to show you how we could find some of these given values. So again, 24.9 now is the mass. Let's multiply that by the height of 70 inches twice, and then divide that by the 173. And again, this gives us 705.3. And so what you're going to notice is that the model that we're coming up with, it isn't going to be perfectly linear. And that's telling me that the values in this table are a little bit rounded, okay? And so really to get an exact value, you would probably want to input all of these heights into a table, all of these masses into a table, all of these BMIs into a table, and actually do a legitimate regression to get the value that you're looking at here. But all I'm going to ask you to do if I ask you a question like this on a quiz or an exam is just to go, well, I see they're all like in that 701 to 706, and depending on the values that you pick, I want you to look at those constants of variation and make an estimated guess, whether it's just an average or if you're like, nah, this is probably a weird outlier, so I'm going to say 705.6. You know, your judgment on that, I think, is totally fine. And then when you're doing that, obviously keep in perspective that you want to be honest with that as far as how you're coming to that. But granted, you know, if you were doing this for research purposes, you would just do the work, do the regression, and then there's not nearly as much criticism that could be had there. So actually, I'm going to switch Y back to BMI. So BMI will be equal to the weight times 705.6 all over h squared. And I think if you actually go look this up, you'll find that this number is actually really close to how it actually is in the real world. So with that said, this is all I have for you for today. I hope that you got a nice, solid foundation on how to find constants of variations for direct and inverse functions, and got a little bit of real-world application associated with those. So with that said, let's do some math.